Hi guys, in this video we're going to hide one image inside another. So that's going to be interesting. We've done something similar earlier with steganography type thing where you hide text in images, which is simpler because strings are not, well, they're not big. When it comes to images, we effectively have two images of identical size and we're going to hide one inside the other. Let's see how that goes. So I've got a template here and I finally upgraded FX tutorials to run on JDK 11, JavaFX 15. All the resource-based tutorials are probably not going to load now. Syntactically they're fine, they're just looking for resources in different folders. So I'll fix that at some point. But for now, I just want to have image 1 loaded. I've got two placeholders, which I'm going to use. Probably resource kitten 1 JPEG. And that loads, that's from placekitten.com, which will give you a bunch of placeholder images. This probably resource, it's external form. There we go. Let's get two images in and then see that they work. And we're going to then add them to the root, give children. How about we make this a vertical box? Add all, new image view. Okay, that's good. So we have two identical sized images. They both have the same, I think it's 600 by 300 width and height. So I'm going to try and hide one inside the other. And the way it's going to work is probably have to play with bits. Okay, first of all, let's define something here. Image width, let's say this is 600. Image height is 300. Let's talk high level to simplify this. Suppose we have a function that gets two images and then combines them into one. So embed. This is going to be image 1 and this is going to be image 2. So this is the source. Is it the source or is it the target? I'm going to call it target because I want to embed inside it, whereas the source is the thing that we're embedding. So I'm kind of flipping this slightly. For now, we're just going to return target itself, so we're not going to do anything to it. In which case, we can do something like, how about we add this to new horizontal box. And then this becomes one row. And then we're going to add another row, which is going to contain two more images. One is the combined one, and then the second one is the sort of decoded one. And then we'll see if there are major differences. So this one is going to be embed image 1, image 2, and this is going to be decode. So I'll have to do this before. Embed it, and then extract it. How about that? Extract it. And then at high level, I think we're pretty much done because there's nothing else we need to do. Embedded. So we just take one embedded image and then we extract from it. Currently, we just return itself. extract embedded. This goes here, this goes there. And we should now have 4 images, 2 identical pairs, or 3 identical images, because the bottom left is the one that's going to contain both images. So we're going to see how that differs with the top left one, which is the original. And then the bottom right one is going to be the extracted one. We're going to compare that against top right, which is the original that we hid inside the other one. So high level, done. Low level. Okay, we need to figure out how to implement that and then that. Let's do a bit of theory, I guess, because we need to figure out how to combine this multiplied by this many pixels in the same sort of 600 by 300 area, because we're effectively in one image going to contain 2 images. And that's a problem that we can simplify. We can simplify it down to just working with 1 pixel at a time, right? Because the number of pixels is exactly the same between 2 images. So we can decompose the problem into a simpler one. We can just focus on how to hide 1 pixel of image 2 inside 1 pixel of image 1. If we can solve that problem, we can then generalize that to all of the pixels that we have. 1 pixel can be represented as ARGB, which is pretty much how JavaFX represents it, I think. And that's 32 bits. That's an int, so it's 32 bits. And it's alpha, red, green, and blue, something that you're probably familiar with anyway. So the alpha channel is basically, well, it's 8 bits. Then we have 8 bits, and then we have, we're just going to write this down as 8888. And that's alpha 8 bits. Then you have red 8 bits. 8 bits give you a byte, and it goes from 0 to 255 to represent that specific channel in the color, which is, again, something that we've worked with. And now we have, so this is just for 1 pixel, pixel 1, and then we have pixel 2 from the other image, which has exactly the same format. So we're effectively trying to fit 64 bits into 32 bits. And here we have, again, 8, 8, 8, and 8. So let's think here. How can we reduce? Because obviously 64 doesn't fit into 32. So we have to play around with bits. I think the most naive, straightforward solution is to just pick the most significant bits from the second image and then replace the least significant bits of the first image, so that you don't have as much of a change in the original image whilst still capturing as much data as you can from the image that you're hiding. Well, we can just get rid of these, right? Because these are alpha. No, but still, because we need to draw this, which is that one. So when we draw that, if the alpha is going to vary, then we're going to end up with some pixels that are potentially fully transparent. It's not something that we want. We can, however, not worry about this one. We'll just assume that every pixel is fully opaque from the image that we're hiding. So we can reduce that, I think, to just 24 bits. And these are the red, green, and blue. Whereas here, we're going to utilize the entire range of 32 bits. Obviously, we can't use all the bits. So if we rewrite this, so it's 1, 1, 1, 1, 1, 1, or zeros, it doesn't matter. I just want to represent this as 8 individual bits, so I can clearly see what we can do. If we take this one, right, this is least significant in here, it's going to change the resulting value by 1 at most. If it's 0, then the difference is, well, anyway, the difference is maximum is 1. These two values, these two bits give us the value of 3, or up to 3. So the difference is up to 3. I think we can manage the differences up to 3 for a specific color channel. Like the difference between red 252 and red 255, I don't think it's going to be that significant. Particularly if we're not going to show the original image to the user anyway. So the user is only going to see this one, like the combined one. And then if we take these bits, that give us up to 7. Difference of 7 we can probably live with. Without this goes up to 15. No, I think the difference in of value 15 is going to be quite significant. I don't know actually, but let's try with just these 3. So if we're taking these out, then per 8 bits, I have 3 bits to play with. 3, 3, 3, 3. So I'm essentially going to be playing with these values and basically kind of saying you're not going to matter to the original image. I can utilize those 3 bits per each 8-bit category. This gives us in total 12 bits to play with. That's not a lot, because that's 24. The problem is still there. We need to figure out how to fit 24 bits inside 12 now. But at least if we drop the right-hand side bits of the image that we're hiding, because these are also represented basically like this, or up to this, in bit form. That gives us 24 bits. So if we drop these ones, then we have 5, 5, 5, 15. No, that's still too much. We have to drop that one too, I think. This gives us 3 by 4. That gives us 12 bits. Yeah, now that could work. Yeah, and this kind of aligns with what I've been sort of thinking. Take the most significant bits and then use the least significant bits. And the good news is we don't have to capture the alpha channel. We'll just assume that every pixel can be fully drawn as 255. But we can't do that with the sort of, which one is it? The target image, because we actually have to draw the target image. So these have to be mostly populated. Okay, so what's the takeaway message from here? How do I turn this into something that I can use? I think I have to write down the full 32-bit version, so I can then map bit indices. This gives me 4, that's 8. So if I just copy paste those 4 times. That's a full range of a single int in Java. That's 32 bits. And we start counting from the right-hand side. So this is index 0, this is 1, this is 2, this is 3, and so on. Yeah, 10 isn't going to fit because it's 2 digits. Or at least this gives me some point of reference. And that is my target image or target pixel. That's the great thing about computer science. If you can manage to simplify a problem down to just one thing, you can then generalize it. It doesn't always work, but it does work in this case. This is target pixel. It's a single pixel of this image. And then we need a source pixel, which is going to be the same. Instead of, but we don't worry about these ones. 1, 2, 3, 4. 1, 2, 3, 4. Because we're not going to capture the alpha channel. And then I can make use of these 3 bits. These 3 bits, these ones, and these ones, because they're on the most right-hand side in their individual category of bits. So the value there, even if we rewrite all the bits, the maximum change in the value is going to be about up to 7. Because 3 bits give us up to 7. Is that right? 1, it's 1, and that's 3, and that's 7. Yeah. And then I can, so I'm not using these values. I'm not using, they say I'm going to drop these ones. Yeah. I think so. We drop these ones. So I'm going to take these 12 bits and put them inside these empty spaces. I like this visual representation. It actually helps me to think. And these are the indices that I need to map against. Okay, so let's start turning this theory into practice and then see if it actually works. We need to be able to read pixels, right? So target, get, reader, pixel reader. I can get an individual ARGB, which is what I've been counting on. It reads the 32-bit integer. I'm assuming I can set it to the source then. So if I do this for image height, for X in image width, and then this becomes target pixel, get X and Y. And then I need source pixel, yeah, I do need source pixel. Pixel reader. And then I need to write it. I need to write it to a new image then. Writable image result. Image width and height. Okay, so where are we now? We got the 2 pixels. We need to then get, well, we do something with target pixel. We're going to put some pixels inside it. Once it's ready, we're going to use result, get pixel writer, and then write, set, yeah, set, X, Y, and then target pixel. And then we're going to return result. Okay, this is looking something like it could work. So I need to take bits 4, 5, 6, 7, and then this is 10, 11. I think I need an int array to store these. So if we store source bit indices, how about that? I think we can do that. And it's going to be 4, 5, 6, 7. That's 10, 11. 12, 13, 14, 15. It's these ones. Then it's 16, 17, 18, 19. Which means it's 20, 21, 22, 23. And then plus 8 gives us 31. Yep, that sounds right. And then I need target. Which I'm going to just reorder this slightly so it matches. Consistency is very important whenever you're doing anything, because it helps you just order stuff mentally as well, because we need to have a good mental map of what we're doing. Otherwise it's very difficult to map theory to practical work. So I need to reuse these ones, the empty ones. So we need to map to 0, 1, 2, 8, 9, 10. 8, 9, 10. This is 15, right? This is 15. 16, 17, 18. And then 3 more. What was that? 23 and then plus 8. Yeah, so this is 23, which means this is 24, 25, and 26. Now we need to rewrite some of the pixels in the target using the source. I think it's going to be something like this, right? If the bit is set in the source, then also set it in the target. And we need to go through all of these. So it's for each index inside here. We can use just one of them because they have to match. I'm assuming they match. It should be 12. 4, 4, 4, 4, 4, 4. Yep. Target bit indices length. Target index. And then source index. If the source index is set, then also set it in the target index. Else, don't set it in the target index. I think that's how high-level code would work, which means we need to just translate that. If source pixel is set at that particular index, which is source index, source index translated, no, it's the other way around. It's just digit 1 shifted by source index, and if that is not 0, what? Can't be applied to int. Wait. if this is int, and this is int, what are you saying? This gives us an int, right? Shift it. Yep, that's happy. Oh, I think it's the parentheses. I need to put parentheses over here. Okay. So the way this essentially works is, in case you haven't done bit checking, imagine we have a bunch of bits like this, and then we're taking one, and then we're moving it by source index, effectively placing where the source index is. So it's something like this. And then that would be the source index, which is taken from here. And the source index is by how many bits we're moving the digit 1, or I suppose in this context is bit 1. And then we're ANDing it, which gives us, well, it's like a normal Boolean AND almost. If it's 1 and 1, it gives you 1. Every other combination gives you 0. So these automatically become 0 because, you know, every other combination of except 1, 1 gives you 0. So these are just automatically 0. We don't know what this one is yet, but these are 0. Now this x is only 1 when this thing is 1, because we know this one is 1, right? And if this is 1, then this x is 1. If this is 0, x is 0. It allows us to check whether this specific bit is set in a given 32-bit int. It doesn't have to be an int. You can do it with bytes too. And that's what I'm currently using to check if the source pixel at that index, source bit at that index is set. Because then you can compare against 0. And 0 in this context is very important because 0 is only 0 when every single bit is 0. Which means if it is equal to 0, then this x is also 0. If it isn't equal to 0, this x is 1. And as I explained, using this x, we can figure out what this one was. So this means source bit at index is 1, set. So we have to set that specific 1 at target index in the target pixel. This is getting complex. Target pixel, we're going to rewrite that specific bit at target index. And this is the bitwise OR, like, again, it's like your Boolean OR, but instead of true and false, we're now checking with against 0 and 1. If it's 0 and 1, it's 1. It's 1, 0 and 1, 1, 1, 1. And the only combination that gives you 0 is if both bits are 0. And given we're shifting 1, whatever the bit was at that index, it's going to become 1. Else, we need to set it to 0. We're going to AND it with, okay, let me write this down so we can see how this would work. Suppose it's something like this. No, that won't work. How about, yeah, that should work. So if we replace all these with just 1, this becomes 0, and then suppose this is 1. And we want to set this one to 0, because the bit at source index is 0, because we're in this branch. So we have to set the target index to 0 in the target pixel. And the way we can do this is we write out our bits like this, so that the one that we want to set is 0 over here. And we AND it. And as I explained previously, gives you 1 only if it's 1 at the target. Otherwise, it gives you 0. So if it was 0, it's going to become 0. If it was 1, it's going to become 1. So these are basically going to be copied fully, except for one single bit, which is that one. And that x is going to become 0, because this thing is 0. Whatever this was, we don't care. It will become 0. Because you AND anything with 0, you get 0 back. We just need to figure out how to, well, we can just flip it, I guess. And then we're going to move it at target index. Yeah, so this is a multi-step one. You take 1, you shift it to target index, and then you flip the other bits. In which case your single 1 becomes 0, everything else becomes 1. Since these values don't actually mean anything, I'm just going to remove them, because otherwise I'll commit this to repository and everyone will be very confused what that was. Source bit index 1 is set. Get rid of this to do. I think we are halfway there. Let's see if this works. No, crazy thing is, I don't actually know if it's going to work, because there is no way to check just yet. I can see that the colors changed. I don't know if you can see it in the video, but if you're comparing it against the top left one, which is the original, we've shifted some colors, and it looks a bit odd. Somebody who's been doing this for a long time, kind of playing with least significant bits, will probably be able to notice that something's odd there. And obviously, if you're running this through computer software that detects these things, it will very easily say that there's something weird going on with bits, potentially. I don't know. But visually, if that's the first image that you've been given, I think it's fine to say that, you know, maybe the source image wasn't that high quality anyway. Okay, how do we extract this now? I think we'll need all this information, more or less. So we're going to create a new image. We're going to do something in there using just embedded. So there's just one pixel, right? It's that one. There's just one single image, which means it gives us back just one single pixel. So these are not needed. And we're going to write this result, and we need a target pixel somehow written. And then we write the target pixel into the result, and everything good to go. So the most important bit is here somewhere. This needs to be rewritten in a way where we extract it's the other way around now, right? So we have to extract these ones from this pixel. Let's call it target pixel to keep with to make it consistent. In which case this becomes source pixel, and we write the source pixel. So we take these bits from this pixel and we write them into these bit indices of this pixel. Right. And then we have to remember the alpha channel, which is just 255. So I'm just going to immediately shift that by 24. This is effectively me writing 111, 111 into the alpha channel. And then the other ones are just not yet written. These ones we need to write, and obviously some of them we won't even touch. They will stay 0 because in the process of hiding an image we lost some bits, which is fine because, you know, otherwise we wouldn't be able to do this. I'm actually interested in a different way of doing this, like compression maybe. If you have any thoughts on how we might do this differently, so we retain as much of the original image, the one that we're hiding, then let me know in the comments, because I'm really interested to see what we can come up with. Meanwhile, I need to, well, the loop stays, I think. It's these ones. Well, this thing stays. And we need to write into source pixel oh, do we just do the same thing but just the other way around? Because we already flipped these, but we need to write into source. That's something I'm confident with. And this is then source index. And these ones become target index and target pixel. Okay, that could be, if this works, then it's much simpler than I thought. Okay, that looks weird, but I think we've done it. So this is source pixel, right? Target index. We're taking target index, which is fine. We're checking if target pixel at that target index is set. If it is, then set one at source index. And then source pixel. Yeah, I mean, that looks right. And we've retained a lot of the original image, particularly given that this was hidden inside this. Not too sure about these artifacts around the edges, but I guess that's what we lost. Okay, I think we're pretty much done here, in which case. So in this video, we looked at two identical size images. We then converted them into a bunch of pixels. We took each pixel individually and disassembled it into an ARGB int, which is one way to represent a pixel. We then took those 32 bits, split them into 4, which gave us the individual channels of a color, alpha, which is basically like transparency, red, green, and blue. And then by playing around with how many bits we can fit into how many bits, we took the most important ones from the image that we're hiding, which is that one, and we rewrote the least important bits of the original image, and thus we've hidden the image from the top right in the image that is in the top left. The resulting image was bottom left, which didn't change much, I don't think, but we've lost quite a number of bits in the original image. I guess that will be more or less important depending on what exactly you're trying to hide in an image. Because if you just want something like this, then obviously we can see pretty much all of the information that was in the original. But if it's some kind of super sensitive like text that can lose a couple of letters, that could be, well, in which case you probably want to hide the letters themselves rather than the entire image. In any case, that was a fun experience playing with bits, and hopefully you enjoyed that too. And don't forget to vote in the community section for future videos, and thanks for watching. I'll see you guys later.